briefly, we are going to talk about Maxwell's equations and really try to understand why they're important. So Maxwell's equations, and in this case the Lorentz force law, these should all look familiar. We have talked about these first three, Gauss's law, the magnetic Gauss's law, and Faraday's law, a few videos ago when it was just three field laws. We saw that Ampere's law, that the path integral of B dot ds equals mu naught I through, had to be modified to actually have this flux term. And so we call that Ampere's Maxwell's laws. So Maxwell's equations, basically he contributed this term and then wrote them all down together. So in a way, it kind of seems funny that we're giving this guy a lot of credit because he mostly just recycled the work of previous people. But there is a lot of value in this. And notice that Maxwell's equations are really just these first four, but we can add the Lorentz force law as well. So there's a few things that are important about this. One is that this actually includes basically all of electromagnetism at once. This is a theory for basically the entire semester. Now, obviously the mathematical interpretation of this is a little complicated. Path integrals might be something that you're not very comfortable with, especially if you haven't taken multivariable calculus, but this is a nice, concrete, concise way to write down basically everything we have studied. And this is very fundamental. These are things that we can kind of argue from first principles based on observations, and then everything else can be derived from these. So the reason that this is important, the reason that it's worth talking about it, is that this is a complete description of our electric and magnetic fields. So again, we've seen other equations, but everything else can be derived from what we just did. This is, again, a mathematical representation of our key ideas. And so my personal view, I want you to be able to actually understand conceptually what all of these are. But being able to write it down mathematically is a big part of physics. Now, this in itself is a hugely important part of classical physics. And classical physics really had Newton's laws of mechanics. It had then electromagnetism, i.e. these things, and then thermodynamics. So we studied a little bit of thermodynamics back in the fall. And so these three pieces are really all of classical physics. Now, unfortunately, classical physics wasn't quite good enough. We figured out that there were some open questions, for instance, in thermodynamics, that led to realizing that there were quantum mechanical constraints we needed to think about. And here in electromagnetism, we got our first hint that relativity is needed. And we've kind of skipped over that, but Maxwell's equations aren't entirely self-consistent if we think about transforming fields between reference frames. And that's a hint that we need relativity. Finally, and the reason why I wanted to talk about this, is that this predicts electromagnetic waves. And in the next video, we'll look at that. But notice, there's the symmetry here. These first two, Gauss's laws for electric and magnetic fields. Okay, there's that. But then notice here, we have that our electric field relates to a time derivative of the magnetic flux, and our magnetic field relates to a time derivative of the electric flux. And from this, we are later going to get electromagnetic waves. So to make sure that we actually understand the conceptual interpretation of this table's in the book, and I'm just using it as is because I think it's a good way to represent this. So Gauss's law tells us that charged particles create an electric field, right? So the basic idea of Coulombic electric fields is encapsulated in Gauss's law. Now, that mathematics is actually only really doable if we have symmetry, but conceptually, charged particles create an electric field. Now, Faraday's law then gave us that an electric field can also be created by a changing magnetic field. Now remember, the difference between these two electric fields is here, our field lines started and ended on charged particles, and here, for Faraday's law, our electric fields were circles, they were loops. Gauss's law for magnetism, instead of in the Gauss's law for electric fields, we have charge enclosed. For magnetism, we just have zero. And that's because there are no isolated magnetic poles. We never find a north or south by itself. And this is actually something that's been experimentally tested, and I could tell you some really interesting stories about that. A professor I worked with is the only person who has actually theoretically sort of discovered a magnetic monopole. but no one, including him, seems to believe that he really detected it. So, interesting story. We've looked for it experimentally, we found one, but because physicists are weird, we don't really believe that we found it. Now, the new thing that we've talked about in the previous video is Ampere's Maxwell's law. So the first part of it, i.e. Ampere's law, simply tells you that currents create a magnetic field. So that's the equivalent of Gauss's law. But then the second half tells you that a magnetic field can also be created by a changing electric field. Now what's interesting is that these two are in the same equation because in both cases you get loops for your magnetic field rather than magnetic fields that are ending on something in the same way that charges did. A Lorentz force law then is kind of that fifth equation that isn't exactly Maxwell's equations, but we still need. And we then see that electric forces are created by electric fields acting on charged particles, and the magnetic force only exists if your charged particle is moving. It's important to remember that the electric force does not increase or decrease if your charged particle is moving. That always stays the same. So again, it's important that you can actually look at these, and even if you don't feel like you can always do out the calculation, understand roughly what these are telling you on the left side, on the right side, and the best case scenario would also be that you know which name goes with what.